more information on contours. Okay, and we kind of covered this. I'm going to kind of go blow past this real fast. Hopefully you will remember what we talked about in class. And let's see, most important thing here is that the contour lines represent the differences in elevations, a coplanar set of points that cut through the surface at different elevations. Okay, and it describes the general lay of the land, and it also can describe the geographical features. We spoke about how a riverbed, the point on the riverbed contours will point upstream. Remember we spoke about that? Also, that I forgot to mention that the flow of the water runs perpendicular to the contours. Okay, so that's another, well, we'll talk about that in a second as well. And if I can get to the USGS map here. Okay, and if you remember correctly, I spoke about the La Conchita slide here. And if we can take a look at some of these contours, if you can see, let me see if I can enlarge this. Here we go. Hopefully it backs out a little bit quick because we're in kind of tight. Okay, there we go. Alright, so as you can see up here in this area, the contours are relatively, evenly spaced apart. And so that's telling you that this area up here is flatter than this. So the contours in this area are pretty dense. And notice the grade elevation. If the sea level right here is at 0, the top of this area right here is at 700. So there's a 700-foot vertical difference in, let me see, this is about, I don't know, about 0.3 of a kilometer. Okay, so it's about a third of a mile, maybe not even that. Okay, maybe a third of a mile. Somebody check me on that. But okay, remember the bathtub analogy? Well, anyway, what if you had a lake that you had during drought conditions that kept on evaporating? You would see the rings around the lake, and in a way, those rings represent contours. Okay, because at every major milestone where you have major evaporation, it will leave one of these rings. So imagine contours as being similar to those rings. And what the contours represent are the difference in elevations. And again, contours are nice round numbers, not, numbers with change like 250.52. I mean, we want to see a 200, 240, 250. So you can see here what the contours represent. And we talked about the steepness of the slope is determined by the spacing of the contours. And here's a gentle set of contours. Looks relatively even, and you can see how that's described here in the profile. And if it's a steeper hill, you can see that the contours are much more dense. And if you have a concave hill, similar to what the La Conchita slide did, it will be steep on the top and then shallower as you approach the bottom. Concave will be the direct opposite. Shallower on the top and then mellow, and then get steeper on the bottom. So it's mellower on the top, steeper on the bottom. This usually represents natural wear, and then it all just kind of comes down here. Whereas this concave could be because of a slope failure. Okay, and here's a cliff, and you can see that all the contours are running into this one point. And if you have sandy soil, just regular native soil, that's probably not going to occur. This is in a case where you have maybe rock or something real stable that's holding that together. Okay, again, streams and ridges, we mentioned that that the V points towards the top, and then where you have two streams meeting at one point and then collecting and going down a larger stream, that usually intersects in an M-shaped contour. Okay, and at hills and ridges, and if the author directs you to page 640, figure 9-7C, you can see how the hills and ridges form U's, whether they're at a hill or in a valley. Okay, and relief features. Okay, we can take a look at a dome, and I was mentioning earlier that if a dome does not have enough detail at the top of the dome, it the contours when you DTM will tend to flatten that area out. So if you look at page 640, figure 9-8, you can see the dome there at elevation 350. How I mentioned how you need to add spot elevations at the top of that to accurately model that. The next figure B, and figure B shows two mounds with a depression right in the middle, and you can see which way the flows goes, or which way the slopes go, according to the image there. And that's called a saddle, okay? There's that little area where it's indicated down, that's the saddle area. Okay, depression, whether man-made or natural sinkholes, are usually indicated by these little ticks on the contour, and you can see that on page 640, figure 9-7C. Actually, I think the author has it wrong here on the slide. Let me change that. Okay, and then he shows the overhang, which we've already seen. So, types of contour lines. Okay, we want the index contour lines. I think, remember, we talked about index contour lines, and typically the number of the elevation is indicated on the index contour lines. In the exercise that we did, the author asked you to put the number on every single contour line, but typically it's only on the major contour lines. And the intermediate contour lines, there's 4 in between the indexes. So let's say the first index is 420. Say we're using an interval of every 2 feet you want an intermediate contour, and every 10 feet you want a major. So if you started off at say 420, you'd have 422, 424, 426, 428. Finally, you'd get 430, and at 430 you would indicate the elevation with some text. Okay, so you would only indicate the text on the major contour lines. The intermediates, or the minor contour lines as we also call them, will not have any numbers. And then they talk about supplementary contours, which we really rarely ever run across. Okay? And here's an example of what we just talked about. Index are the heavies with the numbers on them, and then the intermediates are in between. Okay, we're going to be looking at another figure that will kind of explain this, so I'm going to jump ahead to that image. Well, we're going to have another image in about 1, 2, 3, 4 slides that will explain this. Okay, and a picture is worth 1,000 words. And here's an example. So here we start off at 450, then you have one at 460, and they're operating in tens. So it's 10, 20, 30, 40, and then 50. Okay, so it's 450, 460, 470, 480, 490, 500. So this is every 50 feet, with intermediates being every 10 feet. Okay, the contour represents the elevation above mean sea level, and mean sea level average is at 0 elevation. The next slide is contour line values and different systems you can use. Okay, here's 2s and 10s. Okay, every 2 feet is an intermediate, and then we have 5s here, which are every 5 feet. Then ultimately you get up to 25 feet. Here you got 10s, where it's here you have 10s where every intermediate contour is 10 feet. Okay, eventually getting to 50 feet, and here they're 50 feet, eventually getting to 250. So on this map, it'd be a small scale map in which you'd see a lot of contours, and they would be like every 50 feet. So that would be an extremely high mountain range that you would be looking at. Okay, so you may be asking, well, what contours value should I give it? Should I use 2 and 10? Should I use 5 and 25? Typically, in an average area, you're looking at 2 and 10. So every intermediate contour is 2 feet, and every major is 10 feet. But it just depends on how big your map is. And with Civil 3D, you can change that on the fly quickly. So don't even worry about it. Once you set up your page and you figure out that, oh, I think I could get away with this contour level or that contour, just go ahead and change it then. But back in the old days when we were initially doing things by hand, yeah, that was a real concern for us. Okay, constructing contour lines using traditional techniques, interpolation. We went through that in the first section, chapter 7. So I don't think I'll just kind of gloss over that. You can read through that. And you can read the setup of how this is done, but for our purposes using DTMs, it's really not an issue anymore. Okay, here's just something I kind of wanted to touch on lightly. You have a bunch of spot shots here, and you see the description of these spot shots. You have, this is a summit, so this is the top of a hill. This is a saddle, so this would be in between two summits. And then you have the CL of a road, and you can see that he follows the CL of the road this way. And then he's got a bunch of other, and then he also defines a stream. So you can basically look at this contour line and assign, just doing this hybolically, just kind of sketch, just kind of approximating what the topography will look like without having to do a bunch of calculations. And your map should kind of look like this. With experience, you'll be able to do that. Okay, and here's the again, they're discussing the mathematical interpolation. When I worked out the problems in class, this is the equation I was using after I derived it from the similar triangles. So he just gives it to you in a nutshell. I showed you how to derive that. Okay, so if it makes it easier to use this formula, yeah, by all means go ahead and do it. Okay, another method a surveyor can calculate or get an approximation of where the contour line should lie is that the surveyor lays out a grid, maybe a 10 by 10 grid, 20 by 20, whatever he needs, okay? And he'll take a bunch of shots at every one of the vertexes of the grid, and from there he spots an elevation, and then he can just kind of do the whole eyebolic thing again, or he can actually calculate them out. And here's the process. You can read the process. Okay, here's the grid. So he lays out the grid, and these are every 20 feet. This is the station right here. This is the station call out. 0 plus 0, 0 is 0, okay? And 0 plus 20 is 20 feet away from that spot. That's a way to read these, okay? So this is actually station 100. So then he grids it off by alpha up here. So he says, you know, A, B, C, D, E, F. And that's how he can find himself. So D40 would be right there, okay? So all he would do is once he shoots all these points, he can just kind of, like, again, hybolically just kind of walk his way through there and trace out the contours, which should look similar to this. Just takes a little investigative work and a little patience. So, or that you can calculate it out, but I think doing it hybolically was a little easier. Now a radial survey, basically the surveyor just sets up in a location and shoots out like this, okay? Just shoots out. And that's the radial survey. Okay, he might need several setups to cover a large piece of property. That's what this sentence is telling you. Okay, and if he uses a radial survey to create the topography, what he'll do is he'll set up in one spot and just shoot a ton of spots. Now he could shoot them on a grid, you know, from a radial position, and he would just kind of radiate it out that way. One half a dozen or the other. And now with the new GPS stuff, they just lock it in. He just reads it from the satellites. Wherever he walks, he just marks a point. So that's even easier. Okay. And here the surveyor shoots 1, 2, 3, 4, 5, 6 points, and then he interpolates, similar to what we've been doing. It's the same game. So what he had to do was he had to find the relationship here, find the ratios there, find the ratios across here, across there, across here. If he wanted to, he could cross-check, go back the other way. But it's a lot of a lot of math. Okay, plotting the contour lines. Okay, by doing it the manual method, I've showed you how to do that. Once you find the point on your line by interpolating, you just mark it with whatever contour that you were wanting to establish. Like I think in our exercises we were establishing contour 101, which is the first one. You just mark it, and then you calculate where the 102 is, 103. And you do that for every one of the lines, and then just connect the dots. Okay, but now with DTM software, heck, the data collectors can create the DTMs directly in their data collection boxes. And nice thing about working with Civil 3D is that everything is one-to-one, and we can scale it whenever we want to whatever we want.